you please unmute? Can you please unmute? We cannot hear anything.
Okay. Now can people hear me on the Zoom? Hopefully. Yes. Anyway, hopefully my slides were self-explanatory, so you didn't need to actually hear me, but I'm now I'll do a little recap for those who are on Zoom and got the silent version of the talk. I'm presenting the Cutler method. That's work was collaborative with Meta and Berkeley and Michigan. And the key idea of Cutler is to take an underlying model such as Dino, which has this raw sort of self-attention signal, and use a classic method from decades ago, unsupervised clustering, normalized cut-based clustering, and use it to find these very nice segments. Okay, that alone would be a pretty cool contribution. But what's the key idea of the Cutler paradigm is to actually use that as training data for a direct, efficient end-to-end segmentation model. So the mask cut method generates supervised training data, which can be used to train essentially a mask predicting detector model to very efficiently find these clusters. Okay, let's see my. Great. So mask cut takes this patchified input, the sort of the Dino representations that come out of a VIT that's been trained with the Dino loss, compute a patchwise affinity matrix, and then iteratively find masks using normalized cut. Normalized cut hopefully is the classic method that you've all learned in your computer vision course, pre-deep learning, and it gets very nice segmentation masks. And then what you can do is use this to train directly a mask prediction detection model and very efficiently get very pretty results such as these masks formed here. So this is all completely unsupervised. There were no labels used to create these masks. These are kind of found by the mask cut method and then used to train the Cutler method, which can then be used very efficiently to infer masks on large data sets. So we train Cutler solely on an unlabeled image data, and then we can evaluate it, or they can evaluate it on 11 different data sets, ranging from paintings to videos and traffic images. And each of them, the Cutler model actually significantly beat the state of the art as of the time of this work. So here are some results on paintings, works across a wide number of domains. This is sort of the advantage of using a kind of a pre-deep learning method, something that doesn't actually use labels, but uses notions of grouping and spatial consistency, such as in normalized cut. Here are sketches. The segments look very good. Here are clip arts. Segments also are very, very good. Natural images, of course. Videos. We'll see more about videos in just a moment. Traffic image. So these were still images extracted from videos. They weren't actually videos. Traffic images, and it works obviously on small objects as well. So quantitative results here on many different data sets, significant improvement in performance across a wide number of tasks. Compared to the previous state of the art, the discriminative instances are better, can discover more objects, and have more precise segmentation masks. And often actually find instances that were missed by human annotators and actually were errors in the ground truth. And this can work as a good pre-trained model. Code is available. And again, this is a talk at the main conference. I encourage you to go see. But wait, there's more. I mentioned video. Now here's the extension to video. Also a collaboration with FAIR and my lab. And I think it's fairly straightforward. You can actually notice a lot of the problems that state-of-the-art methods had in video segmentations relied on the fact or were due to the fact that such previous methods often relied on optic flow. And I've been working on optic flow since I was a grad student, on and off. And there are lots of advantages of optic flow, but there are lots of disadvantages of optic flow as well. Lots of cases where it's hard to make sure that the underlying assumptions are held. So we wanted to explore a method that certainly didn't have any labels, but also didn't even use optic flow, and just was like a brute force predict a block of segmented frames coming from a video. And you can see the model, the video Cutler model is based on Cutler. It has all of the benefits of the Cutler model, except Cutler has this key omission of not tracking over time. So we just built a method that could track over time using the same spirit of Cutler. So it takes unlabeled images, it runs dyno features or other features to compute an affinity matrix, and then uses a classic pre-deep learning computer vision technique to cluster or segment those into a set of masks, and then creates a set of really sprite-like, and that not talking about Sprite the soda, I'm talking about Sprite, the ancient computer graphics concept of a bunch of translating objects in a scene, kind of like Mario Brothers graphics. Creates a bunch of synthetic videos, which are just literally objects moving across a scene, and they're moving with linear, like 2D translational dynamics. Completely unnatural, completely unrealistic. This method never sees a natural video, not once, which is really surprising. And from that, we train a mask deformer. We use that as ground truth, make the labels consistent across the entire block of video. And then the model can actually work on natural videos and output consistent blocks. It's obviously not outputting any class labels here. Each one of these is just a different instance because it's a class agnostic video object predictor. So it's really impressive to me that this model is able to do so well on video, despite never actually having been trained even on unlabeled video. Right? It's only been trained on unlabeled imagery, from which it learned this single frame segmenter model based on a normalized cut pseudo labeling of dyno features from which a mask predictor was trained. And then with very, very simple, like the weakest assumption you can imagine for generating synthetic videos is able to actually work on real videos. There aren't too many challenge data sets out there for this. On the one that we found, YouTube Viz, the baselines basically didn't function at all. So we reported this as the first successful method. I guess if some people felt these results were too good. We'll take issue with reviewers number blank and blank. But if results are too good, that should be a good sign, not a bad sign. And this can actually be a very strong pre-trained model in a number of settings. So I'll just point you back to these videos and Video Cutler. I believe the archive is out already. And I think in concert with the revolution that we're seeing with models like SAM, and I'm sure the video extensions of SAM that either are out or will be soon, or other people will also make, I think these unsupervised bottom-up models are a real underpinning of how we can learn without any labels in the future. So now I'm going to pivot a little bit. What time do you want me to actually end? How much time do you want me to recover for the schedule? Will you tell me when I'm done? So now we're going to talk about how language, kind of changing gears. That was bottom up. Now we're going to come from the side. We're going to come from language. Not really sort of using CLIP, but really how can language help with problem specifications? How can language help overcome domain shifts? Right? We know a lot of the problems we have in vision are we test in one situation and a new situation arises that's different, and we have to overcome that fact. And here we want to use language, in fact, interactive language with the person who owns the system. Like, I own a system, I want to classify birds. There are birds out there in the world. Turns out they're land birds and water birds. And I'm going to ask you to tell me whether the bird in front of my camera is a land bird or a water bird, because I have some conservation challenge. And this would be great if you could give me segmented training data, because that's what the task is. But what I actually get in a typical labeled computer vision system are data like this, where I have just zeros and ones, target class is on the right. What's the target class? Well, the model, if you just give it training data like this, how does the model really know if it's, see, the problem is land birds, where do you usually see them? On the land. Water birds, where do you usually see them? In the water. Now, if your test data matches your training distribution, and indeed, in your test data, all the water birds are going to be in the water, this is great. Go ahead and do supervised learning. But in the real world, we may now suddenly have climate change changing our environments, or I might be trying to classify these things in my zoo or my backyard. And I know that actually, whether it's rained or not, isn't actually relevant to whether this is bird type 0 or bird type 1. So how do I do that? I have to go out and collect or manufacture training data to balance this distribution. We don't think you should. We think you should actually do what a human would do, which is if I was training a person to do this task, I would just tell the system, hey, this is a bird task. Don't pay no attention to the background. Or you can expect that the training data has a land-water bias, or all birds can appear on land and water. So what would a human do with this? Well, a human would say, oh, I actually know what birds are. I know that birds exist. And I should probably pay attention to the bird and maybe ignore the background. So that was this first idea. And in fact, and a large-scale vision and language model can enable that, right? Because a large-scale vision and language model, like CLIP, is very good at saying, I know where the birds are. And conversely, I also know where land is, or which is land, and which is water. But there's a trade-off in these large-scale vision and language models. The large-scale models are generally robust to contextual bias, but they fail to do well at fine-grained categories. So if you just want to recognize bird versus cat, pretty good. But if you really want to recognize a specific type of water bird and contrast that with a specific type of land bird, maybe not. So what we did in this first project that we're going to talk about, this sort of 3 micro projects in the language advice section here, is the simple idea that we call GALS, guiding visual attention with language, which is just tell the model what you care about, enforce the model, pay attention to what you care about, and watch your generalization performance improve. And we do that using an attention loss and telling the model, literally pay attention to what the person told you to pay attention to. So this is using kind of GradCam, which is often thought of as an explainable AI method. I'm not that interested in explainable AI for the sake of making people feel good about a model, but I am excited about what we call advice or advisable models, which are when you use these mechanisms to actually make the model perform better. And that's what we showed in this this GALS paper. I think that was at the citation is about to come. I forget which conference it was at. And if you train a model with GALS, instead of attending to the wrong thing that a vanilla CNN would attend to, like the background, it'll actually pay attention to the thing that you care about and do the right thing. And it can even reduce implicit bias in a variety of scenarios, like if you're trying to classify meat versus non-meat, you should probably look at what's on the plate, not what's being served with the meat. I mean, probably, I don't know. And if you're trying to classify the gender of a person, you should probably pay attention to the features of the person and not like what job they have or what tools they're carrying, things like that. So that's GALS. It gets you some of the way there, but let's keep going. Let's keep going with language, advisable language systems to improve robustness. So we'd like to not only tell the model what to look at, we'd like to give the model additional exposure to the fact that this concept might appear in different places. And we're going to do that both textually in the LADS work, and then visually using diffusion models in the last little step here. And I apologize in the interest of time. By the way, when did you want me to finish? 15? Okay. So that's 2/3 of the original time, which is good. I can compress. This is going to be using augmentation in semantic space, and then next we'll augment in pixel space using a different mechanism. So CNNs are great for some things, but they're not so great when the domain shift happens. Clip, zero shot is great, except it's not as accurate overall. What if we use our language to tell the model to hallucinate the training data in a new domain? That's indeed what we've done in this LADS paper. And the LADS paper takes imagery, maps it into the clip space, adds language, accepts additional language specifications for different domains, and then imagines what the training image would look like in that new domain, and uses that as augmentation for a classifier. So we do this using a set of losses that I won't try and explain in detail right here, but there's essentially a class consistency loss and a domain annotation loss. You've seen things like that before in our work and others, but here it's being done in the clip space, and the overall performance is pretty good. In the interest of time, I'm going to skip over this. This cool qualitative result where you look at the nearest neighbor embedding as you map from one domain to the next, and that semantic shift does correspond to a visual shift. The most recent version of this idea that we're exploring is somewhat complementary, but to use diffusion models to generate additional training data to augment your source imagery. You've got an image of a bird near water. You might want to have it also on land or something like that. And so we actually use diffusion models. If you take a diffusion model and use it to generate captions of what the environment is, use an LLM to summarize what environment your actual data describes, you can use that to condition a diffusion model to augment your source imagery with additional imagery that's quite realistic given the other imagery in your training set. So if you're looking at a camera trap, you might have some views which are in a field of dirt and shrubs. You have another one which is near a lake and a field, and so on and so forth. You use those to augment your data using a diffusion model and add those to your training set. It turns out that's can be quite accurate, and much more accurate than other approaches for augmentation, such as you can see here. You can see that so people have proposed the idea of using diffusion models for augmentation, but they weren't conditioned on both language and the previous and the source image. So here, maybe we're actually kind of doing a little bit of a trust region or some sort of constrained augmentation. We're saying, don't augment too far. Don't just make up images of a certain category just on the text alone. It's got to look like the source imagery and have the textual description that you wanted. And if you do that, you certainly get improvement over baseline augmentations. But really interestingly, from the iWildCam data, the Alia method is actually more efficient than, or more effective than adding an equal amount of real data to the test set, to the training set, excuse me. So that's very cool. So this is the ideas from this language. Use language to advise your models. Tell the model what to look at, what to be robust to, and you can either use feature augmentation or pixel augmentation to get there. So these last two themes, I'm going to have to just give you the very high level. I think the first two things we talked about of unsupervised segmentation models, a lot of work there, and I've just summarized a series of papers on language-driven visual robustness. Also want to point out all my co-authors. Now we're going to get to relatively new stuff and stuff that actually dovetails exactly with the previous talk. And I'd first do the modular question answering. It's new, but it's also old. This is collaboration with several colleagues, including colleagues from Google, from Cordelia's group. We've been interested in visual question answering or really hard tasks for quite a while, you know, and you can shove your favorite convent or transformer at a model and see if it can get the right answer. But a lot of really hard questions are not, even humans sometimes don't just get them as reflex, right? There's a line of thinking that says, rather that one was, yeah, that one is reflex. Is there a horse in the scene? I don't need to think too much. I can just probably flash a convnet at it. It'll say horse exists. What about, is there a carriage to the right of the horse? Or how many windows are present above text in the image? And these are all questions that you can answer. We can define them, probably have pretty high iterator agreement, but I don't want to train a convnet or even a VIT to do this. I want to train something that can reason about what's going on in the image. And this is kind of the notion of modular computer vision, modular question answering, modular neural networks, or planning or visual routines. These all goes by the same line. So this is the kind of thing that we like to be able to do. I'm actually going to also switch and share some slides from Carl Vondrek. His group came up with a very similar idea, so I'm going to interleave the results. But here's the demo that he shows. What are these boys eating? If you just run it through blip2, you get muffin. Okay, that's great. Where are the muffins? On the table. How many muffins are there? 2. Okay, unfortunately, you know. So there's a limitation of the brute force approach, where you just smash an image in a query into a neural network. And we've all been focusing on these things in many different ways. And there's another approach, actually, Jacob Andreas, Dan Klein, and I proposed in the Neural Modular Networks paper back in 2015, which is to actually do a kind of first have one module that comes up with a plan. Like if I asked you how many windows are above text, well, you should probably instantiate something that finds text. Then you should instantiate something that finds windows. And then you should instantiate a spatial relation thing between those, and then run that network. And so that's what we did in neural modular networks. We actually imagined you would create a special network that had all those elements that could be jointly trained. And what, you know, fast forward to 2023, what's the new thing that's changing our world? It's these LLMs. And these LLMs know how to code. And it turns out that LLMs that know how to code actually already can solve a lot of those visual skills that we struggled back in 2000, whenever it was 15, to train models to come up with quote unquote program specifications. And Carl's group also has come up with the same idea that my group has also explored very recently. So this is, again, his slide. He started with neural modular networks. This is our work here. And of course, Carl's work is Viper GPT, which is super cool. These last two things came out contemporaneously, independent of each other. But the idea is very cool. It's ask the LLM to give you a program specification to solve the computer vision task. So is the carriage to the right of the horse? I mean, you pick your favorite LLM, it can probably figure out, and these are now our slides. Actually, our paper is being reported at ACL this summer. I think this is from ChatGPT. It knows that there's a way to just take that textual sentence and really compute a semantic parse, if you will, or just directly output Python. Kind of surprised me when I first saw this, and I think there's still a lot of open questions in this body of work that will be hopefully answered in many future publications. But this is cool, right? Already we have, not only do we have visual common sense in CLIP, but we have visual skill common sense in these LLMs. And you get the theory here, which is you can then instantiate a series of primitives like localizing objects, and you can then run the model, actually figure out the answer to these things and say the answer is no. So here's a, are there 4 pandas in this set of images? This is, I guess, a set pictures, and the baseline method says no. But this code-based method that first knows that it should actually run something that counts pandas does better. The model outperforms a lot of baselines and is really cool. And I definitely want to encourage you to not only look at our work that's being reported at ACL, but also look at Carl's work that got out on GitHub sooner and is very, very cool. I think we picked the path of submitting our paper for review at a conference in an NLP journal or an NLP conference, and they have a publication, what do you call it, a bar or block, quiet period. And Carl's group didn't. That was the right decision because I think being out there earlier on GitHub was more fun. But then our paper was accepted and we were able to talk about it. And both Carl's work is excellent and so is ours. I think that's a good lesson as an aside. I encourage everyone to vote at the PAMI meeting against the social media embargo periods. It just creates too many complications. The NLP community has an even worse one than the vision community. But it would be nice to let authors talk about their work honestly and fairly, in my humble opinion. Okay, so I've got 1.5 minutes left. And this will be easy because you all know what MAE is because we just saw the awesome talk before mine. Turns out you can just take MAE, you can run it on figures from a computer vision papers, and that alone can solve computer vision to a first approximation, for a very, very crude first order statement there. We know how to prompt GPT. We want to do vision prompting. This is what we call vision prompting. It's sort of like what we used to call vision analogies. How do we do this? Well, if we believe in all this LLM magic, it's just MAE. And I'm just gonna give you A is to B as B is, A is to B as A prime is to what? And then ask MAE to in-paint the damn thing. Because that's how BERT works. That's how these GPT models work. And this is work that we originally showed last year, reported at NeurIPS 2022. Image in-painting alone gives you a lot of juice. It's really kind of cool and scary how much you can get out of it. As I told you, well, why don't you train it on computer vision figures? So we scraped a bunch of figures from archive and ran MAE on it, randomly cropping figures. That's all we did, maybe with a little bit of additional just unsupervised model. It's not exactly MAE, it's like the BQ GAN version of MAE. I think that makes a small difference, but it's not a big issue. And so you basically reconstruct the model and it can give you answers like that, where you only show it those first 3 tiles and it in-paints that. And there's nothing else. I didn't do language guidance. I didn't do anything else yet. That's just from pixels alone, it can figure out that there's some sort of transformation going on in a repetitive pattern. If all you did was look at computer vision figures your whole life, you would already know what you're supposed to do here, even if you're just an MAE or a BQ GAN MAE. Works for segmentation, works for colorization, works for in-painting, of course, works for edge detection. It worked for some sort of weird things that we thought probably weren't in any figure, in any paper, like shape change, color change, and resizing. It could do 2 things at once, sort of well, but there were places where it would start to fail. And you can read the NeurIPS paper for a discussion of those. And as at the end of the NeurIPS paper, we said, how could you improve it? Well, obviously scaling, everyone wants to scale. More natural image data, it does help when you add some ImageNet data. But more modalities, why don't we actually read the paper and not just look at the pixels? And that's what we've done and recently submitted to a recent conference, and this should be on archive in the coming weeks or sometime over the summer. Because the pixel only in-painting worked, but not always. And so what's actually quite interesting and impressive is a multimodal version of this. So not only do we look at the figures, we actually read the caption. And the caption tells you what the model is supposed to do. Even zero shot without any other pixels, if you just say, left input image, right black and white foreground. I mean, this is sort of like what you might have seen from Flamingo or models like this, but the text prompt actually gets you part of the way there. If you give it text and an image prompt, your results start to improve. And this generalizes to a reasonably wide set of vision tasks, such as the ones that we'd explored before. So I'm out of time, but I think you get the idea. Maybe this is a good place to end my talk, connecting with the previous talk of this, the power of unsupervised representation learning. There are lots of future possibilities, both with raw pixel level, as we're seeing here, but also using more cognitive or planning-based models, such as the modular VQA. And so with that, I'm going to sort of jump to the end and back out of the 4 cool things I told you about: visual prompting using MAE, modular VQA using code generation, talking to your model to tell it what you want. Sort of inverse explainability is advisability, and very, very strong models for unsupervised segmentation that come out of the Cutler family of algorithms. And I just want to thank all my colleagues and students who are mentioned on this slide and all the papers that we have written together. With that, I will end and take a question or two. Thank you.
Again, if you have any question, please come to the middle and speak to the mic. This time we have around 9 minutes for the Q&A.
Yes, I'm not going to try to make this a fight, but so your video cover, if you're going to stay with the realm of not using optical flow, what are you going to do about camouflage, like the really focused data centers, like that?
I think that's the case where you do want to use optic flow. And I didn't say I never want to use optic flow. I think people overused optic flow to begin with. But certainly if you want to do random dot motion or camouflage, it's important. And I think maybe, yeah, but there are plenty of cases where you don't need to use, you know, like there probably are more cases in the world where I have uniformly colored objects moving around than I have camouflaged objects moving around. And so, you know, assuming that optic flow is going to be there is, I think, the problem. And I do feel like yeah, we shouldn't be too negative on optic flow. What we should be, because I think the people who've really done research on optic flow for many years fully understand all these issues. But there's some other people who applied optic flow in segmentation models who didn't fully understand optic flow. And it's those people I think probably should have a balance in their use of the tool.
But this, well, these two guys right here with the paper tomorrow using unsupervised video object segmentation, no optical flow, and full CVPR on camouflage data sets.
That sounds really cool. I'm looking forward to it. What time is the paper?
Mark.
Excellent. Should be fun.
Can I just ask a question about number 3? That's sort of, so I wanted to ask a question on number 3, these visual routines. So it seems you're bottlenecking this reasoning process with these API calls, getting the LLM to generate these API calls and discrete discrete instances of the image. Do you think that's the best that we can do now because of the capability of current vision models, or do you think there's a future in which we can do this all end to end the same way that language models do? So language models can do this sort of reasoning and compositionality just by unsupervised learning at web scale. Do you think we'll get to that kind of vision models?
Probably. And I think the definition of end to end is probably the subtle point. So I would say, can you define end to end to me? Because I would certainly say that this paradigm should be extended to then actually improve the reasoning from end-to-end learning. Now, with the current engineering architectures, that would be prohibitively impossible using the way Code VQA or Riper GPT are architected. But looking at it from a 5 or 10 year perspective, I think these things are going to all push back into each other, and we will learn better visual routine program structures by performing on visual routine program structures. I'm not sure whether Copilot or GPT 3.5, which knows a lot about how to code, might not be optimal yet for learning how to code visual routines. And actually, if you created an environment where it had to spend years in a simulator generating code for various visual routines, it probably would get better itself at that task. Probably is something incomplete about what I just said, but so take it with a grain of salt. But yeah, I think in general, I don't want everything to be fine-grained end-to-end, but I do think everything should be loosely end-to-end.
Thanks for this talk. And in the domain, when mentioning dealing with domain shift issue, you mentioned that augment data by new models, and the pre-S there was like the bird with water, bird with land. But it seems that land and water are some handcrafted things, but in real world, the bird can be with any others. And I wonder, how do you know how many things that we actually create?
I couldn't get the first part. How many? Where might birds exist?
I mean, how do we know we have to create? How we have to augment data like bird with water, bird with land? Why not bird with in the sky or grass or something else?
I couldn't quite hear clearly. Maybe it's a speaker. I mean, are you saying how do you know what domain shift to talk about?
Yeah.
That's part of the problem specification that I think is common for many practitioners in the world. You're working for a car company, you're building a model to detect whether there are defects, and the model suddenly fires off when there's an extra paperclip in the corner of the table that's not related to the part because the paperclip's never been seen before. Well, you say ignore the paperclip, right? I think it's the ability, and I mean, that's the spirit of these unsupervised models. They can suddenly segment entire regions of the image using Cutler or using SAM just by a single click. And so I can refer to any pixel in there and that label will get propagated throughout the whole thing. And the same is true with language now. It's like, well, ignore the extra laptop on the table. It's not important. That's what we want to be able to convey to a machine vision system.
Yes, I wonder if this will make some images, not videos. So I wonder how the performance of sport can be used for textual inclusion.
Well, I think we had a good question earlier that said it probably doesn't work well on camouflage. Who knows? That's probably an area where the performance won't be as strong as on the others. But it does work on natural occlusions because the underlying static image segmenter is actually good enough to track the occlusion over time. So it's not using optic flow from frame to frame to propagate the occlusion boundary, but just the single image segmenter gets the occlusions right. And essentially all that's needed for video processing is just to have label consistency. I think there's some more additional, I think I'm shocked that this training data regime actually worked. And so I would not want to claim that it's optimal. And I'm sure there are some interesting cases of complicated occlusion where this training data won't suffice.
Thanks for the great talk. I have a question regarding the third part, modular visual routines. So the computer vision community was always very, let's say, has had a lot of progress when we had controlled benchmarks like ImageNet. So for this kind of work, I think it's really impressive, like the demos that we can see. But I wonder what you think are the right benchmarks for this kind of work. So like, how can we measure progress?
I need Alyosha here to argue about data sets and benchmarks, but I mean, of course, that's true. I think almost all the good things in the field and only some of the bad things in the field are from data sets and challenges. But it's always a trade-off, a plus and a minus. Well, so anyway, these performance improvements that modular VQA algorithm from my lab or Viper GPT from Carl's lab are demonstrating, those are on existing challenges. I mean, I always find when I look at the examples from the challenge that they don't seem like an interesting problem to me, but they still are challenges in terms of what the criteria that you articulated. So I think we are making progress and demonstrating that, you know, the complicated counting or geometric reasoning.
So it's mainly VQA.
Let me, I think our paper, ooh, something happened. Okay, screen sharing. Anyway, I won't bother. Our paper, I think, is only about VQA. I think Carl's paper shows results beyond VQA. Great. All right, let's wrap it up there. Thanks, everyone.